Swayam Prabha. Digital India. Educated India.
Hi, welcome back to Mechanics and Control of Robotic Manipulator. In the last lecture, we have seen how the Matlab can be used as an efficient tool for finding forward kinematic solution with the help of the arm matrix which we obtained through the Danawitt-Artenberg representation. In the same lecture, I was actually given a small idea. So, with the help of solve command, how to find the inverse kinematic solution if you have forward kinematic solutions are available. In the sense, if you have mu vector, so how we can actually find the inverse kinematic solution using solve. But the solve is not the right option all the time. So, we use actually a numerical method which is faster. So, that would be beneficial when you do for online programming and other things. For example, you have a robot in real time. So, obviously, the numerical method would be little more beneficial than the closed form solution in the you can say computational perspective. So, in that sense, this particular lecture is going to talk about how to use Newton-Raphson method for finding inverse kinematic solution of a serial manipulator. So, here again the same example which we have taken in the original lecture, the same example 2R planar serial manipulator we have taken, and we are actually trying to derive the code with the help of the algorithm which we have come across. So, only change what we made is instead of this delta I, we are going to take the relative tolerance or the arbitrary tolerance, we are going to take instead of delta I, we are going to take delta mu. Okay. That is the only thing, because delta I would not be available to us. So, we would be seeing that what other error we can restrict the delta mu. That is the only restriction we are making it, other than this you can say algorithm which we have written. In addition to that, what we supposed to know, we should have a j of qi and q initial guess and mu. Mu is actually function of q. These all need to be known. So, in that sense, what we can actually see, if we write the Matlab code for this 2R serial manipulator, if the x and y are known, can we find theta 1 and theta 2. So, for that you know this equation. So, where x and y would be given as in the form of function of q, here theta 1 and theta 2. So, if this equation is known, then we can find the Jacobian matrix in the order of, or you can say in the way of partial derivative which I have written in the board. So, now if we see that this partial derivatives are available, can we actually cross check the closed form solution, whatever is giving the result, the same result can be obtained with the iterative method. So, for that we have actually taken the code which is we have already written. Okay. So, you can see that the initial command all are same. So, this is the inverse kinematic solution of a planar RR manipulator with the help of iterative thing. So, only issue is actually I make the editor window closed. Okay. So, this window is actually I closed just for my benefit, so that the display would be very much visible for you. But whenever you run, so you can go to editor and you can actually run or run and advance, but I am going to use a shortcut what called F5. Okay. So, now this is actually the standard. So, now we are actually seen in the lecture. So, where L1 and L2 are actually 1 unit each. So, the same thing we are actually taking it. So, again I am actually seeing one given point. So, in the sense this is in actual we do not know, but for finding the mu value I am actually assuming that this is the actual angle in the sense. So, I am actually making theta 1 is 0 and theta 2 is 90, what would be the mu, that is I am assuming as a given mu value. So, in the sense this is not really there for us. So, for us actually this is obtainable in the sense. So, instead of this relation, the mu a would be straight away given. So, in this case it is 1 comma 1. Okay. So, then what we are trying to do as per the algorithm, we have to start with a guess. So, I am taking a guess as so pi by 3 each. So, after that I am putting the iterative count is actually it can go up to 100 count, but it may not required. I am saying that the maximum count can go to 100. Okay. So, for your benefit I am restricting to 10. Okay. It is nothing going to change. So, then what I am saying that whatever I am actually taking an initial guess, that would be equal to theta 1 of You can say the first value would be theta 1, second value would be theta 2. So then I am actually like derived already with the partial derivative as what you call the Jacobian matrix. So this Jacobian matrix I have derived. So after that I am actually like know the forward kinematic relation, so which will give the mu estimated. Okay. So the mu underscore E is actually like mu estimated. So the mu actual mu underscore A. So now the mu underscore A minus mu underscore E is actually like your delta mu. So that is what I have written as delta. So the delta is actually like actual minus estimated. So now I am actually like putting a tolerance check, so which is actually like 10 power minus 5. So the absolute value is actually like less than, or you can see, or equal to 10 power 5. So 10 power minus 5. So then you break the algorithm. Okay. So break the code, in the sense stop and give the final result. Otherwise you still keep on going. Again we have restricted the total iterative count is 10, right? In the sense, if this is actually like not matching, this will run up to 10 and says that this is the final result, it is not matching. Okay. If this is the case, it will give the final match. So now what we are doing it, so the q I plus 1 is actually like q of I plus inverse of j multiply with the delta. Okay. So you can actually like recheck, this is the code we have actually like written it, right? So this is the same thing. So instead of I plus 1 and I have denoted as q itself. So maybe it may be little confusing for you, but I don't want to keep the count is actually like iterative. In the sense x would be giving a multiple, you can say array, so that I don't want. So q keep on actually like getting changed. So once this is known, I want to actually like plot. So for that I am just drawing a 2R serial manipulator. So which is actually like I take a origin, then the first joint position, in the sense that is the origin, second joint position and the end effector. Okay. This is x0, x1 and x2. Okay. In your case it is supposed to be x0 and x1 is same, x2 and x3. Okay. So then I am actually showing this is the given value and this is origin, how my actual like count is actually like keep changing, that it would be showing it. So right now what we have taken a random guess which is pi by 3 each. Okay. So now if I actually like run through this, okay, so I will see that the output, you can see that. So this is the initial guess, it is actually like keep going, this is the final outcome, you can see it is coming, right. So it actually like gone something and it reached. So I will actually like keep the time little higher, so that I can actually like show it. Okay. So now I put 3 seconds for a delay. So you can see, so this is the first one, this is the second iteration, okay, this is the third iteration and the fourth iteration, it is closer, and fifth iteration is almost reached the relative tolerance which you have given. So now this is 1 comma 1 and you have actually like made it, right. So now if I take the you can say for example different initial guess, I am taking pi by 3 minus pi by 3. So we expect the final solution to be converge, but which solution we don't know. You can see now it started minus pi by 3 in the second joint, this is the second iteration, and third iteration itself it is converge, right. So now for example I am taking a different initial guess, in the sense I am taking this is actually like a 0, the theta 2 is actually like 0, can I get convergence, I can see. So it is something like that. If I start with 0, so you can see your Jacobian matrix is actually like going to be non-invertible form, but still it is actually somehow managed and it is actually like coming, you can see like keep getting it, right. So the third iteration has come and the fourth iteration is not reached. We can see, is there any reason? Yes, we have actually like a reason, right. So it is actually like matrix is much closer because we started with what you call the singular point. So now in order to make it that much more, so I am actually like assuming that this is something like 0.2. Okay. So I am just running it. So you can actually like see, this is the first, the second it is going the exact opposite solution. So you can see like it is actually like ending with something like somewhere where the result is actually like inflection kind of thing. Your initial starting point or the guess is actually like closer to the inflection point. So that's why you can see even the 10 iteration is not sufficient. Okay. So you can actually like see it is keep going. So probably it may end if I increase the iteration count, but you can see, right, it is actually like one iteration to another iteration, it is actually like keep going. So even I will actually like increase this, okay, and I will actually like make this delay probably 2 seconds. So I am just running this, okay. So you can see this is the starting point, this is the next iteration, this is the next iteration, and you can see this is the next, and it is actually like keep going again and again, okay. So you can actually like see it may actually like converge or not, we can actually like see, because we increase the count, right. So now it may be, but the initial guess is actually like around the inflection point, it may actually like take time. You can see it is actually like a converge, right, but it takes more iterations, right. But earlier case you start the initial guess very closer, you got it immediately with a 3 or 4 count, but in this case it is actually like taking a longer time. So it is actually like taken longer duration to do this. I hope now you actually like understand what is this Newton-Raphson method is doing it, and you can actually like change even this target. So for example, this is we have given this way, right. So now I take this as the point, okay. So now in the sense the mu point has changed. So earlier is somewhere here, so now it is changed here. So probably it may be taking the iterative count less, because it is actually like closer, right. So you can see it takes very less. So that is what, so where your mu and where you are starting, so this will actually like increase the fastness, but still you can see the solution is obtained, right, in this case. So that is what we are actually like looking at here. So now I hope you understood what is forward kinematics, what is inverse kinematics, how you can actually like find the forward kinematics using one of the efficient tool called Matlab. The same way you can see the Newton-Raphson method also can be you can say embedded in Matlab, and then you can see the solution is actually like very forward, in the sense it is very easy. I took the example 2R serial manipulator because visualization is easy, but it is not restricted to only planar, or you can say less number of degrees of freedom, the Newton-Raphson method. The Newton-Raphson method can be used for any such, you can say, serial manipulator, okay. So in that sense I hope you are actually like little bit clear. So now even you can see something like close to inflection point I will give, and see that it is actually like keep going. I just to show that. So I will reduce the time, okay. So I reduce the time to 0.1, okay. So I actually like choose some kind of non-trivial, probably I assume this is actually like non-trivial, because I don't know. So you can see like it is reached, right, it is faster. So now I will see this is also pi by 2, okay. So now I am actually like giving, you can see, right, it is actually like getting the solutions. So now I will see if any inflection point I can actually like end up, okay. It is actually like much faster, right, because you have given the initial guess here and it is you have to move here, right. So now this I took it this. So I start the point is actually like a different, okay, this solution. So I just start this. So both are actually like minus pi by 2. So in the sense I start from here, it is reached, right. So now I will start with 0. I am trying to find, is there any inflection which happened to this? Yeah, this is the inflection. You can see, right, even the 20 iteration is not sufficient, where we have started the initial guess exactly opposite solution of this. So in that sense, even if I increase to 50, I don't think it will actually like come, we will see, right. You can see like it is converged to something that, so it is actually like keep getting one another solution opposite, because this is the given point, but you have taken exactly opposite solution of that. So it is actually like a never end. This is another solution which is actually like come under as an inflection. So because of that you can see it is keep coming and it is ending with the same thing, okay. So this is the way we can actually like see the Newton-Raphson method is very much beneficial for us, and you can see that the code what we have written is actually like very straightforward. So, if you want to use any other manipulator, this Jacobian will get changed and this mu vector will get changed, okay, and this would be changed. The remaining everything is same. In fact, this mu actual would be given to you as a direct value. So, for example, so I do not want to put this, so I am just putting it. So, the mu actual is something like 0.5 and 0.2, okay. I am just giving this is the value. So, now I can actually like see. So, I have given this value, you can see it is reached, right. This is the value. Earlier I say 1 comma 1. So, now I have given just a value. So, now this theta actual is not at all playing, this theta actual is just for our reference, okay. This is the value we have taken as a forward solution, this is giving, and I am cross checking the inverse kinematic solution, that is all, okay. So, now you can actually like find the way which is actually like beneficial to us, and with that I am closing this particular lecture. So, now the next lecture would be on differential kinematics, and I hope you have actually like come across the basic description to forward kinematics and inverse kinematics, and you have seen real robot somehow you can say close to this. So, next case we will see differential kinematics, there we will see even real manipulator configuration and see how to arrange the frame and other things, okay. So, with that I am closing this particular lecture, see you then, bye.